Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. In the previous video lecture, we understood the properties of Z-transform. So in today's video lecture, we'll be solving some problems to obtain the Z-transform of a discrete time sequence, and also we'll be solving some problems to understand the properties that we studied in the last lecture. To begin with, in the first set of problems, we'll try to obtain the Z-transform of some useful sequences or some basic sequences. And the first sequence we'll be considering is unit impulse function, defined as delta n. Discrete time sequence x of n equals to delta n. Now we'll be using the standard Z-transform definition to obtain the Z-transform. X of z equals to summation n minus infinity to plus infinity x of n z to the power minus n. X of n is the unit impulse function. So summation will be reduced to summation n minus infinity to plus infinity delta n z to the power minus n. Now delta function exists only at one point at n equals to 0. So summation will not be having any significance because delta function is defined at only one time, that is at n equals to 0. And at n equals to 0, z to the power minus n will be defined at n equals to 0. If we substitute n equals to 0 in the z to the power, then it will be equal to 1. So Z transform of unit impulse function is 1 and its ROC will be all of the z values. For all z values, our region of convergence will be. But the Z transform of unit impulse function is 1 constant. And the second sequence we'll be considering is time shifted unit impulse function defined as x of n equals to delta n minus n naught, and we'll consider n naught to be greater than 0. So using Z transform, the summation will be reduced to only one point now at n naught, because delta n minus n naught will be present at n equals to n naught. It will be shifted to n naught. So z to the power minus n will be the value of this summation at n equals to n naught. So substituting n equals to n naught, the Z transform of the time shifted unit impulse function will be z to the power minus n naught, and the region of convergence will be mod of z greater than 0. For all the values of z greater than 0, this Z transform will converge. Now this time we'll consider time shifted unit impulse function itself, but it will be shifted towards the left side. It will be advanced. So x of n equals to delta n plus n naught, and n naught is greater than 0. And this delta n minus n naught, n plus n naught, will be existing only at one point at n equals to minus n naught. So substituting n equals to minus n naught on the power of z, the value will become z to the power plus n naught, and the region of convergence will be mod of z less than infinity. For all the values of z less than infinity, this Z transform will converge. So in the second sequence, we'll consider positive time exponential sequence defined as x of n equals to a to the power n u of n. We have already solved a problem of this kind. So its Z transform will be defined as z divided by z minus a, and the region of convergence will be all the values of z which are greater than a. And for the negative time exponential sequence defined as x of n equals to minus b to the power n u of minus n minus 1, the Z transform will be same. It will be defined as z divided by z minus b, but the region of convergence for negative time exponential sequence will be different. This time, for all the values of z less than b, the Z transform will converge. Fourth sequence we'll be considering is unit step sequence, which will be defined as x of n equals to u of n. We know that Z transform of the positive time exponential sequence a to the power n u of n will be z divided by z minus a, and the region of convergence will be mod of z greater than mod of a. If in this exponential sequence we assume a value to be 1, then we'll get Z transform of u of n will remain with only u of n, and its Z transform for a equals to 1 will be z divided by z minus 1. And this time the region of convergence for Z transform of unit step function will be mod of z greater than 1. So for all the values of z greater than 1, this Z transform will converge. As a fifth sequence, we'll consider negative time unit step sequence, which will be present on the left hand side, that is from minus infinity to minus 1. So negative time unit step sequence is defined as x of n equals to minus u of minus n minus 1. And again, by the negative time exponential sequence, we know the Z transform of minus b to the power n u of minus n minus 1 will be z divided by z minus b, and the region of convergence will be mod of z less than mod of b. And again, if we assume b value to be 1, the Z transform will be reduced to z divided by z minus 1, and the region of convergence will be mod of z less than 1, just like positive time exponential and negative time exponential. Z transform of right sided unit step and left sided unit step function will be same, but the region of convergence will define the nature of those unit step sequences. Next, we'll consider a sinusoidal signal, discrete time sinusoidal signal, to obtain the Z transform. X of n is defined as sine omega naught n u of n. This discrete time sinusoidal signal will be existing from 0 to infinity. Using x of n in the Z transform equation and applying the limits with respect to unit step function, we can rewrite the summation as summation n equals to 0 to infinity sine of omega naught n z to the power minus n. And expressing sine in terms of complex exponentials, it can be written as summation n equals to 0 to infinity 1 divided by 2j e to the power j omega naught n minus e to the power minus j omega naught n z to the power minus n. Taking 1 divided by 2j outside and dividing summation between both the exponentials, it can be rewritten as 1 divided by 2j summation n equals to 0 to infinity, taking n common on both the exponentials. It will be e to the power j omega naught z inverse to the power n minus summation n equals to 0 to infinity e to the power minus j omega naught z inverse to the power n. Now, both these summations are in the standard Z transform form for e to the power j omega naught z inverse and e to the power minus j omega naught z inverse. So they can be written as 1 divided by 2j. For the first summation, the Z transform representation will be 1 divided by 1 minus e to the power j omega naught z inverse, minus for the second summation, Z transform will be 1 divided by 1 minus e to the power minus j omega naught z inverse. Now for the first term, region of convergence will be mod of e to the power j omega naught z inverse should be less than 1, or mod of z should be greater than 1. And for the second term, mod of z should be greater than 1 again. Therefore, rewriting it for positive powers of z, we can rewrite it as 1 divided by 2j z divided by z minus e to the power j omega naught minus z divided by z minus e to the power minus j omega naught. It can be rewritten as, in the simplified form, 1 divided by 2j, numerator will be z square minus z e to the power minus j omega naught minus z square plus z e to the power j omega naught, divided by denominator will be z square minus z e to the power minus j omega naught minus z e to the power j omega naught plus 1. Now factorizing this and simplifying or combining the exponential to form sine and cosine in the numerator and denominator, Z transform of a discrete time sinusoidal signal which will be existing from 0 to infinity will be given as x of z equals to z sine omega naught divided by z square minus 2z cos omega naught plus 1, and the region of convergence for this Z transform will be or this Z transform will converge for all the values of Z which will be greater than 1. So this is the Z transform of a discrete time sinusoidal signal, discrete time sine function. As a next example, we'll consider a discrete time cosine function which will be existing from 0 to infinity. Now in the same manner, we'll be using x of n, a discrete time cosine function, in the definition of Z transform, and we'll express it in terms of complex exponential again. We'll take 1 by 2 common and divide the summation between both the exponentials. And these two summations are in the standard Z transform form. So they'll be written as 1 divided by 1 minus e to the power j omega naught Z inverse, whose region of convergence will be mod of Z greater than 1, and the second summations Z transform will be 1 divided by 1 minus e to the power minus j omega naught Z inverse, and again for this region of convergence will be mod of Z greater than 1. Rewriting both of these terms for positive powers of Z, it will be 1 divided by 2 Z divided by Z minus e to the power j omega naught plus Z divided by Z minus e to the power minus j omega naught. Again adding both these terms and combining the exponentials in the numerator and denominator, Z transform will be simplified to Z square minus Z cos omega naught divided by Z square minus 2Z cos omega naught plus 1. And the region of convergence will be for all the values of Z greater than 1, this Z transform will be converging. The next sequence we'll be taking is ramp sequence, unit ramp sequence, which will be defined as x of n equals to n u of n. Using this in the Z transform definition, Z transform can be written as summation n minus infinity to plus infinity n u of n Z to the power minus n. And again, because u of n, the lower limit in the summation will be made 0. So terms inside the summation will be n into Z to the power minus n. We'll take n over the power of Z inverse, and we know that the standard geometric series of this form is summation n equals to 0 to infinity n e to the power n will be equals to a divided by 1 minus a whole square if mod of a is less than 1. Using this result for the above summation, Z transform can be written as Z inverse divided by 1 minus Z inverse whole square, and the region of convergence will be mod of Z inverse less than 1, or simplifying it or rewriting it for the positive power of Z, mod of Z should be greater than 1. So Z transform of ramp sequence will be Z divided by Z minus 1 whole square, and region of convergence will be mod of Z greater than 1. So these are some of the Z transforms for basic signals. In the next problem, we'll be using property to solve a Z transform problem. And the statement for the problem is, applying multiple properties, find the Z transform of the sequence defined as x of n equals to n times minus half to the power n u of n convolved with 1 by 4 to the power minus n u of minus n. So let us consider the first part of this signal. There are two terms in the discrete time sequence which are being convolved. The first part we'll consider it as Wn. So Wn will be defined as n minus half to the power n u of n. And we already know that half to the power minus half to the power n u of n Z transform will be Z divided by Z plus half. And the region of convergence will be mod of Z greater than half. So applying Z domain differentiation property for W of n sequence, will get W of Z, which will be the Z transform. For n minus half to the power n u of n, Z transform will be represented as W of Z, which will be equals to minus Z first derivative of the Z transform of minus half to the power n u of n, which is Z divided by Z plus half for region of convergence mod of Z greater than half. So taking the first derivative of this Z transform, or the first derivative of this Z transform will be Z plus half minus Z divided by Z plus half whole square. Multiplying this with minus Z, the Z transform of the first sequence Wn will be half to the half multiplied by minus half multiplied by Z divided by Z plus half whole square, and the region of convergence will be mod of Z greater than half. And second signal in this convolution, we'll consider it as y of n. So y of n is defined as 1 by 4 to the power minus half u of minus n. And we know that Z transform of the sequence 1 by 4 to the power n u of n will be Z divided by Z minus 1 by 4, and the region of convergence will be Z greater than 1 by 4. So Z transform of the sequence y of n, which is y of z, will be defined as 1 divided by z divided by 1 divided by z minus 1 by 4, with region of convergence defined as 1 divided by mod of z greater than 1 by 4. So simplifying this, the Z transform for the second sequence will be written as y of z equals to minus 4 divided by z minus 4, and the region of convergence will be mod of z less than 4. So these two Z transforms are to be convolved now. Actually, the time domain signals were being convolved. So to perform convolution on the time domain is equivalent to multiplying their Z transforms in the frequency domain. So we'll apply convolution property on this, and the convolution property states that if two signals, two time domain signals that we considered here, w of n, if it is being convolved with y of n, then its Z transform will be multiplication of the transforms, Z transform of w and Z transform of y, and the region of convergence will be intersection of the region of convergence of both the signals. So we'll have to just multiply the Z transform wz and y of z. We'll get x of z, which will be defined as x of z equals to, numerator will be 2z divided by, denominator will be z minus 4 and z plus half to the whole square. The region of convergence will be mod of z will be greater than half but less than 4. For the next problem, we'll consider a discrete time sequence which will be defined from -2 to 3, and the amplitude of these discrete times sequence is defined as x of n equals to 5, 2, -2, 1, 1 and -3, and sample at n equals to 0 is -2, so a small arrow has been put beneath it. We'll have to find the Z transform of this discrete time sequence, and we'll have to write the region of convergence for this. So using the definition of Z transform and substituting this sequence in the Z transform and writing the limits will be from, lower limit will be -2 and upper limit will be 3, because the sequence will be existing from -2 to 3. There are 6 samples, total 6 samples. Substituting the values for x of n for each iteration and expanding this summation for -2 to 3, the Z transform will be defined as x of z equals to 5z square plus 2z to the power 1 minus 2 plus z to the power minus 1 plus z to the power minus 2 minus 3z to the power minus 3. Now this is the Z transform for the discrete time sequence defined. Now for z not equal to 0 or infinity, each term in this Z transform will be finite and consecutively x of z will converge. Hence the region of convergence is entire z plane except at z equals to 0 and z equals to infinity. In other words, the region of convergence is mod of z, which has to be greater than 0 but less than infinity. For all the values of z between 0 and infinity, this Z transform will converge. This Z transform will be having a finite value. And the last problem that we'll be considering for the day is determine Z transform of the sequence x of n equals to 0.2 to the power n of u of n minus u of n minus 4. Using this in the definition of Z transform, summation n minus infinity to plus infinity 0.2 to the power n u of n minus u of n minus 4 of z to the power minus n. Now this function, the step function difference between two step functions, can be written as u of n minus u of n minus 4. Now u of n is the unit step function which will be existing from 0 to infinity, and u of n minus 4 is an unit step function which will be existing from 4 to infinity, and we are taking difference of both of these step functions. So the difference of these two step functions will be 1 for n between 0 to 3, for n greater than or equal to 0 but less than or equal to 3, and it will be 0 for n greater than or equal to 4 and n less than or equal to minus 1. So basically in this difference we'll be having only 4 samples which will be present at 0, 1, 2 and 3, whose amplitude will be 1. So because of this, the limits on the summation will be changed to 0 to 3. The lower limit will be 0 and upper limit will be 3, and terms inside the summation will be 0.2 to the power n z to the power minus n. So taking z common, we can rewrite it as 0.2 multiplied by z inverse to the power n. Therefore, using the standard geometric series for finite limits, Z transform will be written as x of z equals to 1 minus 0.2 z inverse to the power 4 divided by 1 minus 0.2 z inverse. The above equation is convergent if this summation n equals to 0 to 3 mod of 0.2 z inverse to the power n if it is less than infinity, and this summation will be finite if the modulus value of 0.2 z inverse will be less than infinity, and this condition states that the region of convergence will be entire z plane except at z equals to 0, because at z equals to 0 it will be 0. So for all the other values of z other than 0, this summation will be having a finite value. So the region of convergence will be entire z plane except at z equals to 0. In the next problem, we'll be calculating the initial value and final value of some Z transform defined. We have studied initial value theorem and final value theorem in the previous class. We'll apply that for a Z transform to obtain initial value and final value of the signals. And the Z transform is defined as x of z equals to z minus 3 multiplied by z divided by z minus 1 and z minus 0.4. From the initial value theorem, or the initial value theorem states that x of 0 equals to limit over z tends to infinity of the Z transform x of z. So Z transform is defined, will apply limiting function for z tends to 0 on the Z transform. So limit, by simplifying this, will get 1 minus 3 divided by z divided by 1 minus 1 divided by z, 1 minus 0.4 divided by z. If we substitute z equals to infinity in this, then the value will be reduced to 1. So x of 0 will be equals to 1. So this is the initial value of the signal obtained by applying initial value theorem. And from the final value theorem, or the final value theorem of Z transform is defined as x of infinity equals to, again this is a limiting function on the Z transform, defined as limit z tends to 1 minus z inverse x of z. Now 1 minus z inverse can be written as z minus 1 divided by z, and the Z transform is given as z minus 3 multiplied by z divided by z minus 1, z minus 0.4. Z minus 1 in the numerator and denominator will cancel, and z in the numerator and denominator will cancel. And applying limit for z tends to 1, the value will be reduced to minus 10 divided by 3. So this is the final value for the signal defined by the Z transform Z minus 3 multiplied by Z divided by Z minus 1 Z minus 0.4. So these are some of the problems. I hope all of you understood all the problems that we did solve today. If you have any doubts, you can contact me. Thank you all.